I'm Lei Bai. Yeah, got it. Recording. Hello everyone. I'm Lei Bai, a research scientist from Shanghai AI Laboratory. So I'm very honored to be invited and present a series of our works about the Fengwu, which is a data-driven global weather forecasting model. So today I would want to mainly focus on four parts. So first, I will give some general background about our team, our works, and also why we work on the Fengwu. And second, I will introduce the first version of Fengwu, which works on 0.25 degree as all other, I think, AI weather models. And thirdly, I will present our recent work, Fengwu GHR, which is the first AI model that works at the 0.09 degree high resolution. Finally, I will quickly discuss some of our explorations on the data assimilation, which is a very critical part of the global weather forecasting system, but had not been discussed a lot in the AI weather forecasting research. Okay, now let's move to the first part. First, please allow me to introduce who are we, since our lab is really newly founded laboratory, so a lot of audience may not heard it. Actually, we invited Nicholas to our lab last year, but many of the audience, I think they do not know our lab. So please allow me to take maybe 1 minute to introduce the lab. Okay, actually, Shanghai AI Laboratory is established in 2021, and of course, it's located in Shanghai, China. And the target of our laboratory is to developing the cutting-edge techniques and solving real-world problems. So although our lab is very young, we already got some very prestigious achievements. For example, our lab won the CVPR 2023 Best Paper Award. So if you know, most AI researchers published papers in the conference, and the CVPR is one of the best conference in the whole AI community. So it's very competitive. And our lab also have released the Intern, which is a general foundation model, just like ChatGPT. It can chat and also can draw some images. And also in the earth science domain, we have released the Fengwu last year, so which I will introduce later. And our lab is aimed to conduct open research with top-tier universities, such as Tsinghua University, Peking University, Chinese University of Hong Kong, and also Nanyang Technology University. We are also working with some institutions to make our, our model to be applicable, such as the CMA and also Hong Kong observations. As for me, I'm now leading the Open Earth Lab, which is formed of more than 20 researcher scientists, PhD students, and also research interns. So if you want to know more about me, you can visit my website, which is this website is www.leibai.site. And since I'm coming from an AI laboratory and as Nicholas had introduced, I'm from the AI community. So you may be interested about why we do AI weather forecast foundation models. So according to me, there are at least 4 core reasons. So first, I think weather forecasting is enough crucial applications, as it's the foundation of the whole operation of the whole world. And different with other science topics, there are enough data in the weather domain. For example, the real observations about both the atmosphere and also the ocean. So this is very important for the modern deep learning based AI. So which we all know that the deep learning is very data hungry. And thirdly, many problems in the weather domain can be translated to an AI task, and especially computer vision tasks, which I have some background from the computer vision and also the time series analysis. So this make AI be a useful tool for the whole process of the weather or the atmosphere and the ocean research, not only for the weather forecast. For example, I think AI could be useful for data downscaling, data imputation, data fusion, data compression, and also forecasting at all scales, for example, from the short term, the medium term, the sub-season term, and also to the climate scale. For example, for the short term, we have seen many works using the video generation method for the radar extrapolation. And also for the medium term, we can, I will introduce many works later. And also for the climate scale, there are many works that they use the AI methods for the ENSO prediction and also the LD predictions. So I think in this domain, we can do lots of interesting works and useful works with AI. to advance the weather and also the climate research. So as said, there are lots of tasks in the domain that we can do with AI. So, but for our team, our current research position is to build the AI-powered foundation model for the global weather and climate forecasting. And then we can use this model to support diverse key requirements, including the short-term regional forecast and also the seasonal forecast, the different kind of applications, such as the wind energy forecast, the solar energy forecast, the typhoon forecast, and also other industries. So for all of those topics and applications, we can see that the medium term to the season term global weather forecasting is at the core position, and that we start in this task. And in fact, global weather forecasting has developed for many years with the physical-based models. And however, it's more and more evident that the physical-based models develop very slow with very high compute cost. So with the rise of deep learning, many institutions are trying to develop data-driven or machine learning-driven weather forecasting models. So just using this slide from ECMWF as an example to quickly showcase the progress of AI weather forecasting models. Because I will refer to many of these works, such as the forecast, the Pangu weather, and the GraphCast in my later slides. As noted, ECMWF started working on this direction in 2018, where they work on a very low resolution and of course leading to some poor performance. Then ForecastNet from NVIDIA first worked on 0.25 degree, which is relatively high resolution in the February of 2022, but they did not surpass IFS errors since only a few variables are considered in their work. And in November of 2022, Huawei further released the Pangu weather. It still works on the 0.25 degree and for the first time surpassed the IFS with AI, followed by the GraphCast from the DeepMind 1 month later. So GraphCast further achieved a better performance measured by MIC and OCC. Our work of Fengwu is released in the April of this last year and got even better performance than all of the previous works. After the release of the first version of Fengwu, our team gets many feedbacks from the weather community, which help us to find many interesting research problems and updates the system in a very quick speed. As can be seen in this timeline, Fengwu is successfully deployed in China Meteorology Administration only 3 months later of its release, and shows its superior ability in typhoon track forecasting last summer. And then in the December of last year, we further released the Fengwu 40WA and the Fengwu ADAS, which focus on combining the data assimilation with the AI forecasting models. Specifically, Fengwu 40WA couples AI weather forecasting models with the traditional data assimilation method, which is 40 variational assimilation. And the Fengwu ADAS try to learn an AI-based data assimilation method. And in the January of this year, we further released the Fengwu GHR, which is the first AI global weather forecasting model that could work on the 0.09 degree high resolution. So this resolution is currently the highest resolution for the global weather forecasting. And all of the previous AI models work on the 0.25 degree or lower. And last month, we further released the extreme version of Fengwu, which further improved the extreme value prediction with the differential model. Okay, so after this general background, let's now look at the details of the first version of Fengwu. So let me first give the problem formulation of Fengwu and also other global weather forecasting models. In this topic, our main objective is to forecast the global atmospheric conditions for the upcoming 14 days. So we are working with a dataset that has a resolution of 0.25 degree latitude and longitude, which is year 5. This means that we divide the whole Earth from ground to the upper level atmospheric into a grid with each cell covering 0.25 degree. With this grid is flattened, it forms just like an image, but it has 3D dimensions. And both our input and output are the global atmosphere data spanning 37 vertical levels from the ground to the upper level air. And we are primarily focused on the key atmosphere variables, including the geopotential, the temperature, the humidity, the component of wind, and also the V component of wind. Accordingly, we are also predicting 4 surface variables, including the mean sea level pressure, 2-meter temperature, 10-meter U component wind, and 10-meter V component wind. This adds up to a total of 189 variables in this model. So as you may be aware from this task description, Fengwu is actually dealing a very large amount of data. Even though the Fengwu V1 is works on the 0.25 degree, there is 0.7 gigabyte data for each time step. And if we predicting 14 days weather state at a 6-hour time interval, it will sum up to about 40 gigabyte data. So if we directly optimizing this task as the other AI method, it's almost impossible due to the current hardware limitations. To track this challenge, we adopt an approach similar to that of physical model. Fengwu is trained to predict the atmospheric variables for the next time step based on the current moment. Then we can achieve long-term forecasting during inference through an autoregressive method. As depicted in this diagram, we can generate xi plus 1 with the input xi. Then we can feed the xi plus 1 into the Fengwu model. It could then generate xi plus 2. By doing this iteratively, we can generate all the predictions in the following 14 days with a fixed time interval. To get the model we want, there will be 3 key challenges in my point. First is how to represent the very high dimensional weather data. As I have said, there are 189 dimensions in the dataset. So for which we introduce the multimodality design. Here, the multimodality design refers to the fact that we employ 6 separate encoders and encoders to encode and decode different atmospheric variables at multiple levels and surface variables. So as shown in this figure, for the geopotential, humidity, U wind, V wind, temperature, and also some surface variables, we design a separate module or a separate representation network for them. And in this way, we can learn the interactions of each variables at different locations more efficiently. And then to learn the interactions among different variables, we further add a cross-matrix fusor, which is another transformer to learn their correlations. And the second challenge is how to optimize the network very efficient. So due to the varying difficulty, importance, and precision of predicting different variables, using the mean square error as the loss function might lead to the model to optimize positions and variables with large errors, while neglecting those with small errors. In the atmosphere predictions, normalized data such as the 500, it normally requires higher precision. Use MIC for optimization might not be effective as the error is already very small in the normalized context, causing the model to not optimize these variables. In the previous GraphCast model, they manually assign weights to the loss of different variables to address this problem. However, it needs a large amount of trial and error since there are 189 variables to optimize, and also it's impossible to assign weights to each location. So in this case, we approach this issue from a multitask perspective. We treat the optimization of each variable at each location as a separate task, and we use the multitask learning method proposed in this paper to automatically then learn the weights from the loss function. So in this way, our method can automatically then learn on weights adapted for each location and also each variable. This would help the network to optimize better. And the third challenge is how to achieve very long-lead forecasting. As I have said, we have the input of the current atmosphere, but we need to generate a prediction for the following 14 days, which is, for example, if we have the 6-hour time interval, this would be 56 steps. So how to achieve very long lead forecasting is a very key and also specific challenge for the weather forecasting. This challenge, to solve this problem, previous works employed 2 strategies. So one is autoregressive fine-tuning, which feeds the output into the model to generate the predictions at the next time step, and optimizing all predictions at the same time during training. Autoregressive fine-tuning is employed by forecast and also by GraphCast. So the difference in their implementations is just that forecast only conducts 2-step fine-tuning, the T+1 and the T+2, while GraphCast conduct 12-step fine-tuning with many optimization strategies. However, we found that it's still hard to implement the fine-tuning with more steps, for example, 50 steps. So we need a better method for long lead forecasting. And the second strategy is training with a larger time step. This is employed in Pangu. Different with our work and GraphCast, they are trained with which are trained with a 6-hour time interval. Pangu is trained with a 24-hour time interval, which significantly decreases the number of iterations during inference, and that decreases their error accumulation. The drawbacks of this strategy is that it requires the training of multiple models, which involves more computation, because this method cannot be generalized to some scenarios that do not allow the training of larger time steps.
So can I ask a question?
Yeah, of course.
Just to clarify, so your aim is to do forecasts on with a 2-week lead time, right?
Yeah, 2 weekly, and also if we finish this work, we want to forecast 28 days or even longer. Yeah.
So, and my understanding, this is what I wanted to clarify, is that rather than learning the map that maps you from weather today into weather in 2 weeks in one go, so really like the flow map from here to here, you learn it successively over small time steps. Is that correct?
Yeah, this is actually similar to the physical model as I have introduced here.
Yeah, you had this. And how
model two,
what is the time scale from one to the next?
Currently, the time cycle is 6 hours for our method and also for other methods.
So why don't you go straight to 2 weeks? Why don't you learn that big map?
Yeah. I think this is a very good question. Let's go to this slide. Actually, you can see that Pangu learned the 4 models. For example, the 1-hour model, 3-hour model, 6-hour model, and also 24-hour model. So this is very similar to your idea, right? Directly learn a 24-hour model. And we have tried this, and we found that the optimization is very hard because the correlation as the current time step to the 24 hours or to 2 days or even 2 weeks, the correlation among the data is very, very weak. So it is possible, but very hard to learn the network. If we can learn the network, I trust the performance is definitely very good.
But if you were interested in kind of not sort of weather forecasting where you want the small details, but some kind of coarse-grained weather patterns, let's say El Nino or something, do you believe then you can learn this sort of larger coarse-grained map and learn sort of those? I mean, just a question.
Yeah, that's a very good question. Actually, for the ENSO, right? For example, ENSO forecasting, this model, I have a student working on this domain, and we found that AI model can predict 19 months lead with a 0.5 ACC. So this is because the model directly takes the monthly mean of the current time step as the input and directly predicts the output after the 19 months. So this could work for the SST because the SST, the pattern could be rough. It's kind of similar, it's simpler.
Yeah, it's some coarse-grained pattern, right?
Yeah.
Like a macroscopic
pattern. Yeah.
Thank you. That clarifies a lot. Thanks very much.
Yeah. So, but I trust if we can directly optimize, for example, 2 weeks for the whole atmospheric data, the performance would be definitely very good. But currently, we cannot do that.
No, that makes sense because of the correlations, as you said. Thank you.
Yeah. Okay, so let's move to the presentation. So here is just a strategy to achieve long lead forecasting. So just how to fine-tune the network, just as the forecast of GraphCast. But we design a very new strategy. So in this strategy, our model, we think the main problem for the model to generate accurate long forecasting is that the model hasn't encountered future prediction status during the training, because during training it only sees the T+1, so the error accumulation is very fast. And the solution I think is very straightforward. We can simply expose the models to these data points. This involves adding our predicted data to the training data set for further model training. So if you see this figure, you can see that when we input xi to the model, it could predict xi plus 1. Then we store the xi plus 1 to the memory, to a memory queue. And in the following iterations of the optimization, we can retrieve this data from the memory and use it as input to the model. And then use the ground truth data correspond to this input as a label to optimize. In this way, we are actually doing the fine-tuning as a GraphCast, but without gradient passed in the whole data. And this brings many benefits. First is that we can store many data in this memory queue. From xi plus 2 to xi plus t, and this can be very long. So we can actually, optimize very long term forecasting. And the second, since the memory queue it could be stored in the CPU memory, in the memory of the computer, so not the GPU memory. So we can use a very large amount of memory, and we can make this memory queue very large. And this helps us to achieve a very good long lead forecasting performance. And we have conducted application studies to evaluate the effectiveness of the replay buffer in boosting the forecast skill. We compare the performance of both Fengwu with and without the replay buffer mechanism. As shown in this figure, covering different variables, the system forecasting performance decreased significantly as the time increase when the proposed replay buffer is removed, indicating that the replay buffer is very crucial for improving the accuracy in the long lead weather forecasting. And okay, so with all of the above model designs, we conduct large-scale training on the ER5 dataset, which is the 5th generation ECMWF reentity data for the global weather. And we use only one out of 6 portions of the whole dataset to train the model, because our model is a 6-hour time interval. And also we use the data from the past 37 years data for the training, and use the 2-year data for validation, and the data from the 2018 for the testing. And the whole training of the model costs 32 A100 GPUs, and it trained for 17 days. And in this slide, we just present the MIC of Fengwu and also the GraphCast, which is the best AI forecasting model previously in the year of 2018. And we can see that the black line is the MIC of GraphCast, and the red line is the MIC of Fengwu. And the lower MIC normally means the better prediction performance. As we can observe, Fengwu generally achieves better performance than GraphCast, which is the best model, AI model previously. And more specifically, Fengwu achieves better performance on 80% of all the variables reported by GraphCast. And the performance gain is more obvious from day 3 to day 10. And specifically, Fengwu reduced forecast error by about 10% compared to GraphCast, and by 19% compared to the F5 errors. And we also report the ACC of both Fengwu and GraphCast, and the observations are just similar. So I will not repeat the analysis in this slide. And based on all the previous analysis, I summarize the core benefits of Fengwu to 2 points. So the first one is that the long lead skillful forecasting. So according to the ACC of Z500 bigger than 0.6, and also the T2 meter ACC bigger than 0.6, we can say that the weather forecasting lead time of Fengwu is beyond 10 days, and this had never been achieved previously. And we can also see that the development speed of the global weather forecasting is significantly boosted after AI is applied. It cost almost 10 years to improve the skillful global weather forecasting skill, only with 1 day. But now we may only use several months to improve the skillful forecasting lead time with about 1.2 days. And another benefit is definitely the efficiency. So this should be true for all the AI models, not only for our work. So in our experiment, we found that the Fengwu can generate the predictions for the next 10 days of all regions in the world with only 1 GPU and within 30 seconds. But for the physical models, it requires 10,000 nodes running about 1 hour. And after I have mentioned, the Fengwu had been deployed in CMA and also other weather forecasting administrations. So we could present some operational forecast results of the typhoon track. So this slide shows the results of a typhoon named Kanu with our model deployed in the Shanghai Meteorology Administration. So in the left figure, the red bar shows the prediction error of Fengwu at different times, while the yellow, green, and blue bars correspond to ECMWF HARRIS, NCEP, and also GMA. The errors are calculated with the same samples, so we can observe that Fengwu almost always achieve the best typhoon track performance. And the two figures in the right part present the predicted track of Fengwu, ECMWF, NCEP, and also the beta track at two different initial time. We can see that Fengwu can accurately predict the two sharp turns in the Kanu, this turn and also this turn, demonstrating its super reliability. We have also got some real-time evaluations results from the HKO, where they evaluated Fengwu with both the ECMWF initial field, which is this line, and also the NCEP initial field. Please note that Fengwu had never been trained with the NCEP data, but we can see that the performance of Fengwu with the NCEP initial field is still good, although the performance is not as good as the Fengwu driven by the NCEP field. And also the typhoon track performance with both an NCEP field and also ECM field is better than the other models. And the HKO also gave us a very interesting case about the typhoon genius. In this case, traditional numerical weather prediction models forecast the potential tropical cyclone to form and affect the northern part of South China Sea over the mid-autumn festival. But the Fengwu correctly forecast that the typhoon will not form. Okay, after the deployment of Fengwu, we actually got many feedbacks, and the most normal one is about the resolution. So many weather forecasters said that the resolution of Fengwu and also other AI models is not enough. So we put a lot of efforts to improving the resolution of Fengwu, which results in Fengwu GHR, the first AI model that works on the 0.09 degree. So before introducing the Fengwu GHR, let me first introduce why do we need a forecasting model with high resolution. So by this figure, we can see that from the 2-meter temperature at Shanghai, the temperature of different locations vary a lot, even though the distance between the 2 points are only 80 kilometers. With a model at 0.25 degree, which is roughly 29 kilometers, we cannot accurately predict these detailed weather distributions, making modeling the weather at a high resolution necessary. And also, if we can modeling the atmosphere dynamics at high resolution, we can model the dynamics more accurate, which potentially could help us get better performance. Besides, high resolution can also reflect the extreme event at a smaller scale, as shown in this figure. So, however, we all know that developing the high resolution weather forecasting model is always very challenging. As can be seen in this figure, ECMWF actually takes about 10 years for updating their system from the 0.25 degree to the 0.09 degree. This because the high resolution brings significant high memory and also the computer burden. And also, even for the AI models, if we develop the model with the transformer architecture, it will require 80 times computation if we directly updating the data from the 0.25 degree to the 0.09 degree, if we have the data. But unfortunately, we do not have enough high resolution global atmosphere analysis data, because as we can see from this figure, EC only start to run their 0.09 resolution model from 2016. From 2016 to now, we can only get 5 or 6 years data for training. But for the year 5, we can use almost 40 years data for training. So we can say that the high resolution global atmosphere analysis data is very rare. To solve these two challenges, our core idea is decomposing. So we can decompose the complex atmosphere dynamics in the very high resolution data into two parts. The first part is modeling the atmosphere dynamics that can be captured in the lower resolution data. So in this way, we can reuse the network we previously learned in the large scale ER5 data to help decrease the requirements of high resolution data. So this is make our method data efficient. And the second part is modeling the atmosphere dynamics that only exists in the high resolution data. So to do this, to do this in a very computationally efficient manner, we propose learning only a small amount of new parameters, which is called the regional enhanced simulation module in our paper. And as we can see in this very simple diagram, in the math model, we learn the math model in the ER5, so which have sufficient data. And then we learn the regional enhancement simulation module only in the high resolution data. Because this module only have a smaller amount of data, it can be learned sufficiently. And since the math model pre-trained is pre-trained on the ER5 data, it cannot directly process the high resolution data because they have different resolutions. So we propose a spatial identical matching, which divides the high resolution data into low resolution chunks to enable the transfer learning and reuse the math model learned at the 0.25 degree. As we can see in this diagram, spatial identical matching divides the data grades according to their spatial region resolution. For example, the grade at the top left corner are arranged together to a new low resolution data. Then we can feed this low resolution data into the low resolution model, for example, learned on the ER5. And after the data is processed with the low resolution model, we can then combine them together back to the high resolution and use them to fine-tune the regional enhancement simulation module in the hidden dimension space. And except for the above core ideas for enabling the learning of high-resolution modules, we further propose a LoRa-based fine-tuning strategy for achieving very long-lead forecasting. Here we need to say that if we only need to achieve a high-dimension model, we can combine the previous strategy that I have mentioned above with both the full fine-tuning. We can also combine it with the repeat buffer I have mentioned above. That's okay. So that's the key technique for the high-resolution modeling. But here, LoRa is just for the long-lead forecasting. As shown in this slide, the core idea of LoRa is kind of similar to Pangu, which assign a specific weight for each time step. It's also very similar to your idea. That is, we can learn a specific network for each time step. For example, we can have a net 1 to map the x0 to x1. We can have a net 2 to map x1 to net x2, and we can have a net 3 to map x2 to x3. But have a very large network for each time step. It's very hard to optimize. And so we introduce a LoRa method that is widely used in the currently LLM models, which just add a very small amount of model for the network for the optimization. This will make the optimization very effective. Okay, that's all the core design of our method. And after the method design, we need to train the network. So in this part, our training data is not only the ER5 data, but also contains the operational analysis data from 2016 to 2021. And the spatial resolution, as I have said, is 0.09 degree. And for the vertical levels in this paper, we only use 13 pressure levels because we found many AI models use 13 pressure levels. And for the variables that are consistent with Fengwu V1. And for the testing, we use the real-time analysis data as the input, which is exactly the same as the alpha Harris to make the comparison totally fair. And for the evaluation, first let's see the evaluation on the graded data of 2022, where the blue line corresponds to alpha Harris and the red line corresponds to Fengwu GHR. So because the alpha Harris is the only model that works on the 0.09 high resolution. So here we can only compare to the alpha Harris. And we can see that the Fengwu could achieve better performance for all variables regarding MIC and ACC metrics. And in this work, we also evaluated the bias and activity, which are also very key metrics. As we can see from the top two rows, we can see that the Fengwu normally have smaller bias than alpha Harris, meaning that the Fengwu had less symmetric error. However, as all the other AI models, the activity of Fengwu is not as good as the F model, which I think we should further improve it in our future works. And for this work, because our model and the F8 Harris are the only two models work on the high resolution. If we want to compare our model with other AI models, we need to introduce other labels. So in this work, we conduct large-scale evaluation on the weather station observations, which are the golden ground truth for the weather forecasting evaluation. In this work, we use the observations for more than 18,000 stations downloaded from NCIE and evaluated the model from July to December of 2022. And these figures give the evaluation for each month. And we can see that the Fengwu GHR significantly improves the predicting performance at all these times than Pangu and also F8 Harris. And we also conduct two case studies. The first case study is about heat waves. And this heat wave is happening in 2022 in Chongqing. And the first column is the prediction of Pangu, and the second column is the F8 Harris. The third column is the Fengwu GHR, and the final one is the analysis field, which can be treated as ground truth. And we can find that the forecasting of Fengwu GHR and the F8 Harris is definitely more fine-grained than Pangu. And also, by comparing Fengwu GHR and F8 Harris, we can find that the extreme value predicted by Fengwu GHR is better by the F8 Harris. And we also compare a case study for the winter storm, which happened in the North American in the December of 2022 at New York. And the study is conducted with one weather station and through 2 months. And through these 2 months, we can find that the overall performance of Fengwu GHR is much smaller than FS and also Pangu. And also, if we're looking at these very rare extreme events, we can find that Fengwu could actually predict these extreme storms with at least 9 days lead time. So this is much better than the F8 Harris and the Pangu weather. Okay, so after these two weather forecasting models, in the last part, I also like to briefly introduce some of our recent work on combining Fengwu with the data assimilation, which are just the primary explorations, and they are not completely finished. So here, the data estimation is always a very core component of the whole weather forecasting system. It maps the sparse and noisy observations from different kinds of devices, such as the weather stations, the aircraft, and also the satellites, to a dense and graded analysis field. So to improve the data assimilation quality, the background predicted by the forecasting model is also used as an input, as shown in this pipeline. Before 2023, the data estimation methods such as 4D versional estimation only works with the physical model. In 2023, although we have seen the deployment of many AI models, including our Fengwu and our Fengwu, but these AI models do not work with the data assimilation module because it still only relies on the data analysis field generated by the traditional physical weather forecasting models and data assimilation pipeline. This brings two drawbacks. First, the whole system is still very complex with huge computation cost by running the physical model. And the second, the excellent forecasting ability of AI weather forecasting model are not used for generating the background. It will decrease the quality of the background and thus hinder the upper bound of the whole system. To solve the problem, we are working on coupling AI forecasting model with the data assimilation from two views. The first view is that we try to directly coupling the existing AI forecasting model with the traditional data assimilation model, such as the 4D versional data assimilation, which is very straightforward, but it needs some engineering. And the second pipeline is that we try to learning an AI-based data assimilation method and coupling it with the AI forecasting model. Currently, we do not know which method is better because we are only working on the simulated data and not working on the real observations. So for the Fengwu 4D VAR, the formulation is the same as the existing system. According to this formula, the 4D VAR aims to get the best estimation of the current atmosphere field, which is x0, and with the predicted background xb, and also the sparse observation y tau. Here, M could either be the physical model and also the AI model to generate the background. And as I have said, for this work, we just need to combine the existing AI model with the 4D versional method. So there are just lots of engineering works. For example, how to guess the B metrics and how to get the R metrics and how to implement the the 40 version method in the GPUs, because the AI method can run in GPU very fast. So lots of AI works, but I think it's very, very meaningful work. And the second one is for phone ADAS. For phone ADAS, it just try to learn a network that can take the sparse observation, for example, the YT plus delta tau, and also the background as the input and generate an analysis. So this problem can be also formulated as an AI task. And after we generate analysis with the network, we can then feed the analysis into the phone model. And the phone model can make the prediction and can also generate the background. So this whole network or whole system can work in a self-contained manner. And this is the general network architecture for the ADAS model, which I will not go into the detail, just I think because it's just a network, but I will give 3 core information. The first one is that we introduce the quality mask to reflect the data quality of each point. While the mask is 0, it means that there is no observation in this grid. And the second, we use the gated convolution network to process the sparse input, which only merge the information from the grid that have observations. And thirdly, the label here is used during the training is the ER5 data, which means that the analysis, the quality of the analysis will not better than the ER5 data. So it's still constrained, by the currently physical model, I think. And for the experiment, both phone 40W and phone ADAS currently are evaluated on simulated setting by sample data from the ER5 at observations. And currently, experiments are conducted on the 1.4 degree with iterative estimation and forecasting running, as I have mentioned, over the whole 2018. We can see that AI-based assimilation and forecasting system can achieve stable status. So these experiments are conducted for 1 year. So this means the days, the x-line is the days, and the y-axis is the MIC and the bias error. And we can see that the black line is the error for the background, and this blue line is the error of the analysis field. And so from these 2 errors, we can see that the data estimation of both 40W and the AI model can improve the quality of the analysis data. And here,
sorry,
we also
for which system did you show this? For the one where you use data set AI only in the forecasting model, or
sorry,
showing
this actually is for the results of phone ADAS. So if you want to
and how does it compare to the one where you do not use the AI to do the actual analysis?
Yeah, it's just the background generated by phone. Yeah, from this slide, you can see that there are 2 data we can compare. So the first is background. The background is directly, input the initial state into phone, it can generate background.
Sure, but what happens if you now do normal 40W on that background?
Yeah.
How does that look like?
Yeah, for the 40W, the performance is similar. So I do not put that figure in this slide. If you want to get the results, you can, you can find that in our paper. I will give the paper list later.
Okay, thank you.
Yeah, the results actually is very similar. And here is a visualization where I show the Z500 of this time point, and including both the ER5 data, the background generated by phone, and also the analysis data. And I also show the observations, the data points of the observations, and the background error, and also analysis error in this figure. And we can also see the analysis increment, and which we can find that it very corresponds to the background error very well. And we can also see the analysis increment at the observation point and also at the unobservation point, which we can find that the model can estimate the data to the unobservation points. However, although the results looks very promising, but I need to see that there are many limitations. So the first limitation is that all my previous results are simulated observations instead of the real observations. This brings 2 issues. So the first is that the simulated observations are not consistent with the real, the locations of the simulated observation are not consistent with the real observations, because in the real scenario, there are less data in the ocean. but more data in the land. So this should be addressed later. And the second one is the data quality are not consistent with the real observations. Although our e-premise have added some noise to the data, but we found that the real observations have much larger error in our later analysis. And another very important limitation is that currently we did not consider the satellite observations, because satellite observations are not the the ZQUVT, this kind of observations. They are different. So how to include the satellite observations is also another issue. And the third limitation in our draft is the resolution is very low. But in last month we have extended to the 0.25 degree. So this limitation is solved. Okay, so in summary, I will give some takeaways. So the first is that about our lab, the Open Earth Lab is focusing on the cross-discipline research on AI and Earth science, and we are very willing to conduct the collaborative research with the audience. And the second is that Fengwu is an AI-based weather forecasting model that can generate a skillful global weather forecasting with 37 vertical levels beyond 10 days lead time. And the paper is in this link. And the third one is Fengwu is computationally efficient, which can run on a personal laptop with only 1 GPU card and can generate 10 days predictions very fast. And you can use this link to access the model of Fengwu. And the first one is that about the Fengwu GHR is an advanced AI model with the highest resolution for global weather forecasting. The draft is here, and we will give the open source code later. And the final is about the data assimilation, is our preliminary explorations. We have, and the link is in this part. And the last page about the paper list I have mentioned above, including both Fengwu GHR, the Fengwu 40W, the ADAS, and also some tropical cyclone prediction tasks, and also for the precipitation nowcasting model, and also the extreme version of Fengwu. And we have also used Fengwu to improve the quality of the weather data, as I have mentioned previously. The first one is use the diffusion method to improve to conduct the downscaling of the weather data in the eastern area. And another one is we try to use the NERF method to downscaling the weather data to the station level. Okay, that's all. Thank you. So if you want to know more of our work and get the updates, you can find my go to my website, which is this one, leibai.site. Thank you.
Thank you very much, Lei Bai. That was very exciting. In particular, how you pushed this up to 0.09 degrees. Really, and I mean, I have a few questions, but how you did that exactly, because I think it's quite ingenious. So let's see whether